Okay. Xianglin,
Yeah.
please.
So the paper I'm going to present today is actually the second paper, but it's highly related to the first paper, and I think the first paper might be the one that we actually interested about.
Yeah. So yeah, Xianglin, please.
And the first paper is published at ACL 2021, and it's an oral paper. And the second paper is published on EMNLP 2021.
Okay, so since we have an alternative, we have a change for the group meetings. So the paper we selected, it becomes more general. It is not specific on the concrete work guiding the research, our individual research, but it will point out some broader or bigger pictures. And here, I just read the news. We're finding that the China is now lack of the energy, right? Sometimes we have a breakdown, but the energy problem is actually the world problem. And people looking to the green energies, and consider the AI will be everywhere, and AI, the power consumption of the AI models will be increased, right? So that'll be a big problem, and how to build energy efficient AI models might be another channel for us to look into. But we know that we kind of lack of the manpower to look into this space, or even lack of the energy or time to look into this space. But anyway, it's good for us to have a picture of what this related work is. And now we have ACR papers, and some researchers have already looked into these areas. We can have a check. Okay, Xianglin, please.
And all the 5 authors are from Stony Brook universities.
Yeah, this is a small university, but it's very strong in terms of the computer science.
And the first author is now a postdoc at University of Washington, but I think he finished this work when he
was a PhD student.
I'm not sure, maybe in the transaction time, I'm not sure. So the background of this paper is that we know that there are more parameters for NLP models, and the question is how to accurately estimate the energy consumption of those NLP models. And 2 possible solutions was here. So first, you might, one naive solution is to directly monitor the energy consumption from hardware, but this solution would need the exclusive access to hardware and some detailed instrumentation. And if you base on those software methods, their research on this part saying that it's not accurate enough. So the goal of this paper is to design a solution that can first accurately estimate the energy consumption of an NLP model, and also with little overhead on the side. Otherwise, you don't know whether the energy consumption is caused by your NLP model or the method you are using. And the second one is that they hope their solution should provide an interpretable energy analysis. And the last goal is this method should be extensible and generalizable.
Okay, please go on.
And then let's look at the high level overview of this work. So first, they abstract the model into this tree structure with the, how to say, this yellow part to be some machine learning level operations, and with the blue part to be a model level. So the yellow part should be model agnostic, but the blue part should be related to some NLP model specific module. And then they do this multi-level energy prediction. That means first they predict the node's energy consumption, and then build this bottom-up prediction until they got the energy estimation for the overall model. And then the third step should be end-to-end training, because each time they predict the energy consumption for some single model. It contains some trainable weight. And they do this end-to-end training to learn the trainable weight. And in the fourth part, they can do this prediction. That's the overview of how they estimate.
Sorry, so the prediction here is for the energy consumption.
Yeah.
So it is going to estimate for each component here, focusing the tide is actually a model, right? So
what is the model?
So here, if we have energy consumption, so the input is actually a model, and output is that, and how likely and how much energy is required to train such a model or run such a model.
I would say run such a model.
To run such a model.
I think they focus on the inference part.
And here, the input is actually a BERT model, right?
A BERT, yeah.
A BERT model, and this BERT model is decomposed into
tree structure.
Yeah, the tree structure, and the tree structure, and the leaf node is actually the ML level component, and the intermediate is actually a module level, and here where the prediction. Yeah, well, this is actually the target model, right? And the consumption prediction is on each individual node.
Both on individual nodes and on the overall model.
Okay, so this is actually a profiling, right? It's more like a kind of profiling, so that for each module, so for each component, and how much consumption it will be. So yeah, it's very much like the efficiency or the runtime profiling. But for traditional programs, the profiling is looking to, for example, we write a Python program. The Python programs is consist a lot of functions, and the functions will call the functions. And in this case, existing profiling technique will record an instrument to measure how long will each functions take during the whole execution. So maybe this perspective is very similar to that kind of profiling. Okay, let's keep going on.
And first, for the model tree abstraction, actually they divided it into 3 levels. The bottom level is math level. That means some operations like addition, subtraction. And then they have this machine learning level, which is the yellow part inside this picture that we already talked about. There are some model agnostic operations. And then the first level is module level. Those blue notes denoted some BERT specific module. And how they decompose the model into this tree structure is by this just-in-time instrumentation.
So is they still using the instrumentation to measure the consumption or measure the runtime? By right, the instrumentation means that we instrument the additional code to instrument the additional
Otherwise,
measurement.
you don't know what's their leaf node and what is the model structure.
So the question here is that we are looking to the energy consumption or the time consumption.
Energy consumption.
So if it's the energy consumption and the instrumentation is based on the software code, right?
But that's how they do this tree abstraction.
Tree abstraction.
So your input should be a model directly, and then use this instrumentation to get this structure, this right? Otherwise, how do you know there's some linear layer, some?
So given the models focusing on TensorFlow, the PyTorch, we definitely can decompose it.
Then in that case, you need to analyze the code directly.
Yes. So,
but their method is to do instrumentation to get this.
So it means the structure, it does not allow us to apply the source code analysis on the model.
No, they are not doing that.
Yeah, I'm still trying to understand the problem background, right? So assuming that we have already trained a model, whatever TensorFlow, PyTorch, Keras, whatever it is, and so when we load the model, we can already be able to build such a tree, right? So suppose we load a CNN model, ResNet is 15, 20, and we can just decompose it into the CNN layers, and one layer by another layers, and we're still able to build such a tree model. The only reason is that we need to build such a tree model without a source code level because maybe the model has already been running, or whatever the reason.
I'm not so sure about that, but after they got this structure, and then for each node, they would run it maybe 20 or 50 times and calculate the energy consumption and then divide it by 20 or 50 and get the energy consumption per run.
So the run is just taking for the ML level. So for example, we got a linear, we get
both ML level and module level.
Okay, maybe you can keep going on, then I may digest a little bit with your follow-up slides.
And then how they do this multi-level energy prediction is that for the leaf node, what they do is, so first they would just do what I just said. They would run it multiple times and get the energy consumption and record all the features per node, like the batch size, sequence length, flops, memory bytes, and those information. So they are the features for each node, and it should be a ground truth. And then apply this linear layer and get the energy prediction for the leaf node. And why they choose this simple?
Sorry, I would like to interrupt a little bit. And can you repeat the definition of the feat?
Feat, that's feature.
Oh, it's a feature. Okay.
Oh, feature. Yeah. So they get the feature for one node.
Get a feature for one node. Okay. Also, basically, they would like to predict that given a node in the model, and they, based on the CPU utilizations, memory utilizations, to assume the energy consumption, right? And the P is actually energy.
Yeah, the E is energy and P is not sure what is P, but a prediction.
Prediction, yeah. And but the problem is that when they do maybe I asked the question too early. On when they have the predictions, but on each machine, the energy consumption is a little different
So that's why they have this CPU utilization, memory usage, and memory bytes. That's different for each machine, right?
Yes, they are different, but you can see a CPU of i4 is definitely different, consume different energy of a CPU of i9, right? It will have the CPU device type as a feature. I assume no, right? And also there's the GPU energy. It's joule. It's a joule as a unit, right?
But I think before prediction, they will run the model on the machine they are using and get those features.
And what is the unit of the predicted value? Unit, yeah. Yeah.
The
joule. Right. Is that the joule?
Is
here you can see.
I know.
I'm not sure whether I have the good correct pronunciation.
Yeah, me too.
But the point is that the same CPU utilization and the memory utilizations and their consumed energies will be different from one machine from another, different from one machine. Yeah, right. So and how do they balance it, or they are only working on a single machine?
No, they construct, actually later I'll talk about it. They construct a data set. And I think they use two machines to construct the data set.
I think maybe their model is machine specific.
Oh,
Right. So that means so once we
no,
got
they are not machine specific. That's one of the limitation of this paper.
they are or they are not.
So this is machine specific. Yes.
Yeah, I think they are this model is machine specific.
Yes.
But it might be generalized a little bit. I'm not sure whether we can calibrate on or standardize or normalize energy consumption from one machine to another.
So if you construct this data set using a lot
just like complexity, just like the calculation of the algorithm complexity. And why we need an algorithm complexity, because the runtime overhead will be different from one machine to another, right? Suppose I have super powerful machines, it will be run faster, but it will have a crappy computers, it will run slower. But nevertheless, we just have the computation. We have the computational complexity. And here maybe there's a chance to invent the units of the energy consumption, just like the energetic complexity or the energy complexity, that in contrast to the concepts of the computational complexity. But I still have not the very concrete idea how to estimate this. Maybe in terms of the instruction level, because each instructions takes energy to run, right? And that will be, but for different machines, they will take different kind of energy to execute a certain instruction. But if we come down to this instruction level, maybe it is out of the reach of the machine learning expert. It's more towards the programming languages or software engineering research, more toward the job of the researchers in software engineering, and maybe more towards programming language. Right, the compiler people are quite interested in that area.
Yeah, and let's continue. So why do they use this simple model? Is first, it's interpretable and it costs little time or little overhead. And for non-leaf node, one very naive solution is for it to sum over all its child node energy consumption. But in this paper, they are afraid that some error might propagate to the final results. So instead, they add some weight or coefficient, and this coefficient also contains some trainable weight. So,
okay.
Yeah.
Okay, so this basically a linear combination of linear combination, right?
But they have a 10. So this is
okay. So they delinearize the expression. Okay.
Yeah. So that's all, and then they conduct this end-to-end training, because using for each model they record the energy consumption for the old model or the model, and then they use this loss to train the model.
The ground truth. Okay.
So this is the ground truth of energy consumption for each subtree, and they have this prediction, and they minimize the difference between them.
Okay, so why we design the loss in such a way? Why not just the sum of the difference? And why we need to normalize into the GS square?
I think they want to have more accurate prediction on leaf node, because for the for higher level node, GE should be larger, right? And they divided by a larger value means they focus more on the leaf node. That's my interpretation of this function, this formula.
Okay, so that makes sense.
And for the prediction part, so for once they got the software model, they will first do this just-in-time instrumentation and get the tree abstraction structure, and then they run on monitor to get the feature values, and then in the third step that will predict the energy consumption.
And that's all?
Yeah.
The approach ends here.
Yeah, approach ends.
So the approach is very, very straightforward. There are nothing special, but they're looking to a very, very different area. Yeah, you can see just in these areas, even the simplest model, if we apply the simplest model on some very established area, this paper can never be published, I feel.
But the point is you need to design a very simple model with little time overhead and a little overhead. Yeah, and they should make it interpretable.
You can look into it in approach. Isn't it very hard? I don't think so, right? Right. And also the question is that once get a model, if we already have the model, why bother to using Git instrumentation to have the structure? So that is my puzzle. We can already have the structures if we have the source code model, right?
Yeah.
Okay, so any specifications on do they specify on how they measure the hardware consumption, because the final unit is supposed to be joule, right?
Yeah, actually they have one section to talk about the hardware configuration, but I didn't look into detail about that.
But anyway, I think they need some special measurement for the energy consumption.
So I think they should just record the energy in watt. It's the pronunciation, right? So
but how do you know the energy is consumed by? I don't understand. So but how do you know that energy is specifically be consumed by the model?
So they have a monitor to record that.
Let me think about it. So they supposed to be have some differential analysis. So because if you run a computer, right, the operation system would still take the operation system will still take the consumption, and also the some bootstrap and the network will all takes energy, right? And how do we calibrate those energy consumption to make sure that this part of the consumption is definitely be consumed by the model execution, right?
They do have a section specifically justifying that, but I didn't look into that.
Okay.
Yeah, and they do the experiments on 2 PCs. The configuration is listed here. And for the NLP model, they choose 1, 2, 3, 4, 5, 6 models as subject model. And they also compare their method with one software baseline called Experiments Impact Tracker. And yeah, they also talk about other implementations to get the ground truth. But sorry about that. I just skipped. And then they claim that they construct a data set for energy consumption with different batch size and sequence length. Like they run 3 models and get the ML nodes energy consumption and module nodes. Yeah. And I think they use this data set to train their prediction model. And the first research question is how accurate is IrEne-viz. So for the software baselines, they can only predict the overall energy consumption for the model. So they compare their method with this baseline, and their error rate is much lower than baseline for the model level. And then they also conduct the module level prediction and machine learning level prediction. actually the error rate are quite low, but they cannot compare the method to other baselines because no baselines has addressed this problem before for the ML level and module level.
Keep going on.
And then second is they wanted to ask, are those design necessary, like the end-to-end training process or the tree structure or the learnable weight necessary? And then they conduct an ablation study to show that those 3 steps are necessary. Yeah.
Okay, let's keep going. So I think that doesn't matter so much. Okay.
And then the third research question is, what is the application of IrEne-viz? How can you interpret this energy analysis? So first, they claim that this method can be used to find the bottlenecks in transformer models. And they found that for like robota, self-attention takes the most energy. And
okay, so keep going on. I think for here, since if we want to optimize or compress the model, we should always to consider both the energy consumption and the role it played in the whole model, right? So we can never to drop one layer just because it is very energy consumption. We may look into details to have a balance.
At least you can know which is the bottlenecks. And the second application should be task accuracy. Should be so the background of this application is that when you wanted to use some model to give some prediction, and there's a trade-off between energy consumption and task accuracy. They found out that if the task accuracy is high, then this model should be more energy computation expensive. And if you have these measurements, and then when you are given an energy budget, then you should be able to select the most accurate model or optimal structure.
Okay, so I just get a last point, or anyway, you can keep going on. I will give my comments at the end.
Yeah, and in their discussion, they're also saying that it's a problem for unseen hardware, and one future work should be like predicting other training dynamics like the time or other evaluation.
Okay, so I have my comments here. So it's the end of the presentation, right?
No, I also have an overview for the second paper.
Okay, thanks.
Yeah, so because this is the overview of this research work. So when you have some model as input, and then you should run the JIT tracing and get feature, and then to estimate, and then training an estimation model, and finally to predict energy for each node. So that's the overview. And then for their visual design, they wanted to design and front end. And when you have some queries, they should go through this process and get the energy prediction and then put it on the front end. So that's the overall visual design. And actually we can check this. It's a very simple front end. So you can choose which model you want to visualize, for example, here, and choose the batch size, sequence length. And then they show you this tree structure. And for each node, you can see the energy consumption features along with the predicted energy. You can also expand it, and the bottleneck would be highlighted in darker color. Like this. So that's their design. Yeah. And in the end, they are saying that the extension to other hardware and other models has not been implemented yet, but it's future work. And yeah, That should be the end of this.
Okay, thanks, Xianglin. I think this the final demonstration helps a lot for me to digest more of it. So this idea is very similar to the profiling idea of the traditional software. In the traditional software, for example, we will write a programs to run slowly. So we want to know which part of the code or which line of code make it very slow, right? Maybe we have a loop and which runs for hundreds of thousands or 100,000 times, and the loop is actually unnecessary. Maybe there might be a chance to trade the space for the time, right? So this is basically the idea of the traditional program runtime profiling. And here is more, it seems to me more like when we consider the software model, the deep learning model as a traditional software program, and we want to know which component, maybe it is a multi-layer on component, maybe it is a BERT component, or it might be the other, the query component, which takes a lot of the energy. I have my comments here is that once we get the energies, we usually want to have the so-what questions. So once we have for the software for the traditional software, we know this function is really time consuming. And our idea is that we want to reflect it, right? So maybe there's some way to refactor model in terms of its energy consumption. The direction is more like seeing that whether there's a more energy efficient modular, right? So suppose for example, we find that the CNN is actually really time consumption, or maybe the BERT model or the self-attention. You can think about it. Self-attentions will require us to learn the relationship between every sibling network or feature, right? In this case, whether we will ask question whether it is worthwhile to capture all the relation of features, since it seems to be quite energy consumption, quite energy consuming, right? So what is more energy efficient modular can we design? So this is maybe one direction. Another direction, think about is that the really energy consumption process might be the model training instead of the model execution. So when we have the model execution, we just need to have one pass. For example, when Yufan is training an object detection model, it takes, or we train again, right? Dr. Xiaoyan actually also have the experience of train again. The training of the games takes a lot of times, but running the game is actually okay. So whether there's any chance for us to understand, to improve the energy consumption during training, for example, we're not looking to the forward process, but in the backward process. But this is more looking to, this might also look into the computational complexity of model training. Yeah, maybe I need to think more about in these directions, but overall, how to address the efficiency problems of model training and model execution might be a way to go. And I think the importance of the AI models might have a higher priority comparing to the efficiency improvement of the traditional program, because training the programs is more like to replace the programmers to extract the rules, right? Okay, thanks, Xianglin. It's a really an articulated presentation. So the next presentation is supposed to Yufan and Changsheng about the quantum programming. Hello, Yufan.
Yeah, hello.
Oh,
Let me share.
Okay, yeah, Changsheng, you will be the one to present, right? This is the first time Changsheng take part in our this meeting. Yeah.
Oh, yeah.
This first time, okay.
Let me first share my screen, and I'll give a brief introduction to the quantum computing concept and a few basic simple examples of how to program it. And after that, Yufan will give a demo on the grooves algorithm, which is can be used in like database indexing. Let me share my screen first. Yes. Can you see my screen?
Yes, we can.
Can you see the slide?
Yes, we can.
Okay, let's start. So I would like to give some basic concept of quantum programming and quantum computing, and what's the difference between quantum computing and classical computing. So let's start with the difference between quantum computing and classical computing. So let me first clarify that classical computings are great, right? Our whole internet and even the video games, and for example, even our Zoom meeting now is based on the classical computing. So classical computing can solve many problems, but they got their limitations. So what are their limitations? For example, if we're going to solve an optimization problem, like arranging seats for 10 people, the possible combinations of this problem will be like 10 factorial. It's like 3.6 million of possibilities, right? And with the number of guests, every time a new guest joins the table, the complexity of the problems grows exponentially, right? And same as when we want to solve the problems in chemistry or biology, like a protein simulation. Take a very simple example. If we want to simulate an enzyme, we need to consider each and every electron and atoms in the whole protein, in the whole moleculars. This problem also grows exponentially, right? So classical computings, when we try to solve this exponentially growth problems, they face the limitation because they cannot be scaled to even to the real world applications. For example, the protein in the right is a very simple enzyme that only consists of 3 clusters. And the fact is, it's the biggest protein we can now simulate, even in the most powerful supercomputers nowadays. So how to use quantum computing to solve those problems that is impossible for classical computings? We first introduce 2 basic concepts. First is the superposition. Superposition is like a weighted sum or linear combination of 2 or more quantum states. A quantum computer with n quantum bits or qubits can exist in a superposition of all 2 to the n of its computational basis states. And to comparison with classical states, we only got 0 or 1, right? And in quantum states, for like a 2 qubits quantum computer, we can have a superposition between 0 and 1. And I will give the example later. And the second concept is entanglement. For example, we got 2 qubits and entangle them together. That means measuring the first qubits can tell me about what will happen when we measure the second qubits. The state of entangled qubits cannot be described independently of each other. That's a basic properties of quantum theories. And how to solve the problems using quantum computing. Like, for example, you take a qubits. You're going to take the qubits into a superposition of all possible states and all the possible configuration, and then you encode the problem into your quantum computer. And then you can apply a phase of each of the states. The phase, as you know, is a kind of access to how the qubit is facing towards or the center of that sphere. And you saw it's like when the two waves are in phase, their amplitudes add, right? And when the two phases are out of phase, they cancel. It's like you have a noise canceling headphone. So you're creating noise. What you are doing is you're creating noise that is exactly out of phase with the noise. So you can cancel the noise by adding them together, and you can cancel the noises wave, the noises amplitude, right?
And by the way, Changsheng, have you prepared a few questions to ask the audience?
Yes, I will do the QA part in the examples, in the demo,
okay.
right?
Okay, sure.
I'm now introduce some basic concepts, so helps you to understand those demos.
Yeah, and here maybe I feel a little bit lost a little bit. And can you be specified on the relation between those pictures, right? So each circle is actually a qubit. Am I right?
No.
It's not a qubit.
You mean the circle in the whole sphere? In the sphere, those rings are the possible states of those qubits.
For example, for the first circle, which is in red, and they have maybe 5 rings there. It means that this sphere has.
Okay. This plot is just a workflow of how we can design a
quantum computer,
quantum algorithms, or how can we use quantum computing to solve the problems. And this sphere, this qubit space is very complex. I will give some simple demos in the later.
Okay, so is there a definition of the phase?
Yeah. So the phase is like we can encode those problems into the phases, and different qubits, they got different phase, and we are going to solve. Then we use interference. So basically, you amplify some answers and you cancel other answers eventually, and eventually arrive at a solution. So it's just totally different to the ideas of how we design the classical algorithms. So let's continue. So how to learn quantum programming? So there are 2 basic counterintuitive principles of quantum physics. These are first, a physical system in a definite state can still behave randomly. And 2 systems that are too far apart to influence each other can be correlated to each other. Remember these 2 counterintuitive principles, so it will help you understand those demos. And how can we run quantum programs? We can first use simulators on classical local computers or cloud services, like the quantum cloud provided by IBM, or even NUS got its own quantum computer in the Faculty of Science. So it's a small scale, only got 2 qubits volume, but this idea is the same as the state-of-the-art quantum computers. So basically, they are using the superconductive circuits and to build the a simulation of quantum qubits of the qubits. So the idea, the difference between simulators and the real quantum processors is that simulators random states are generated by the pseudo random generator. We all know that the randomness generator in our modern computers, they are not genuine random, right? They are pseudo random series, in fact. But in real quantum processors, their randomness are guaranteed by the physics design of the circuits. We can do our prototyping in the simulators because it's much more faster, and we can even run these simulations in our own local machines. And after we do the prototyping, we can do the test on the providers' real quantum computers. And in fact, those big companies like IBM, they got real quantum computers in clusters for free access to students and to researchers. So I encourage all of you to have a try after this this workshop. Yeah. So let's start with some demos of the quantum programs. So there are three ways to write a quantum program. The first is we can use a quantum composer. It's basically a GUI-based programming interface. We can just drag and drop those components and build our quantum programs. It's very intuitive, and because nowadays the quantum programs are very simple, so it's possible to build the whole program using this GUI interface. And also we got the QSkit Python library, and also the OpenQSM for is the quantum assembly language. The three demos here represent the same program. Yeah, we can see if we're just using the quantum composer, it will be very intuitive and easy to implement. So before the demo, I would like to give you some basic components of how we design the program using the composer. First is the reset.
Hello, Changsheng. Can you explain what does those programs do? Like what is the input and what is the output? And
let me do it later.
Okay.
So this is the reset operation. Basically, it provide you can see it as a variable. It's provide it's not it's like a variable or constant. It starts with 0, and you can change it to 1 using the NOT gate. And the measurement.
Sorry, what is NOT gate?
A NOT gate is, you know, the NOT logic. You flips the 0 to 1, 1 to 0.
Here, so anyway, I'm no expert here. Once we have a variable in the classical machines, a variable is actually can be considered as register if it is just put into the CPU.
Yeah.
When the programs, we have a variable corresponding to a memory address, right? So, and for this quantum, the basic elements is not for bits, it's for qubits, right?
Qubits, yeah, qubits.
And for these qubits, and how do we represent the memory address, or we can just
we can see those qubits as the classical registers before we give them superposition. So here the 0, you can say it's like, you can see it as a classical register. And later we will show that after we put the 0 to a hard mode gate, it will become qubits in superposition. We can see is this 0 as a classical register. Okay. So it's
can you specify the definition of superposition?
Okay, I will do later.
Okay.
And the measurement is how we get the results. We all know the very famous example of the Schrödinger's cat. Do you guys know it? The Schrödinger's cat. It's basically we put the cat in a box with some toxic radioactive mass, and the cat is in a status that's between death or alive, right? And before we open the box and measure the state of the cat, its state will be in a superposition between death and alive. And once we measure it, it becomes a concrete value. So the measurement is like we put these superpositions to like these values with probabilities. And what is a superposition? We can create the superposition using the hard mode gate from 0 and 1 to the plus and minus. So let me start with some examples. My screen. Can you see my screen of the quantum computer?
Okay.
Yeah. So as I mentioned before, we start with a reset. It provides a variable, and we can see once we define a reset, once we define the Q register, it's a reset and represent 0. It will show that we got two probabilities, probabilities on 0 and 1, and because it's not in superposition, its probability on 0 is 100%, right? And now if we want to measure this value, measure this quantum register, its results will be always 0. And we can change the random seed. We can say, even though we change the random seed, its result is always 0. And if we give a NOT gate, it will change flip to 1. It's very simple to understand, right? And now we introduce the hard mode or H gate to make the quantum register into a superposition. Yeah, let me delete this NOT gate. And before measurement, we can see before measurement, a qubit in superposition ideally have half possibilities on its states, right? It's 50% on 0 and 50% on state 1. And it's worth to notice that this is probabilities. And if we change if we do the measurement now, we can see it changes from the probability to frequencies. So if we do the measurement, its frequencies on a single measurement will be 100%, 0 or 1.
Maybe wait, Changsheng. So let me raise the question here to audience so that I hope that some of you still follow. So in this case, suppose giving Changsheng suggestion, if we apply an edge operator on here, and then we change the random seed, and what is the probability that after the measurement, the outcome is 1? Have I made my questions clear?
I understand your question is basically like
my question is that suppose we change another random seed. So here, Changsheng will change the random seed, right? This is supposed to be what Changsheng is supposed to be before Changsheng was applied the operation. And what is probability that the bar of 0 will be changed to the bar of 1? Anyone would like to have a try?
Anyone have ideas?
What does edge operation do again? Sorry.
Is it change the variable, change the qubit into a superposition, right?
I still don't understand what is superposition.
Okay.
It's like we put a concrete value of a variable into a randomness. Like we change from the certainty to uncertainty.
Okay.
So now after the H gate, the states of the quantum register can both be 0 and 1. And if we do the measurement, we inference it, we do the measurement, it will show one of the possibilities in a single measurement. So my question is,
but the Schrodinger, according to the Schrodinger's cat, but we never know whether it is 0 or 1 unless we measure it, right?
Yeah. Now we can change the random seed to do multiple samplings. So do you guys have any idea when I change
Darren says it's 50-50.
Yeah, 50-50. Let me.
You can try 10 times. You can try 10 times. You can count how many.
Yeah. Now I can change the random seed. You can see, it changed to 1, and it's changed it again. It's still 1, and I can do it. I can run it on a real quantum computers now. Like I can do 1,000.
It is not a simulator. It's a real quantum computer.
Yeah, I can do it on a real quantum computer, but its queue may take a long time. So I do some of the.
Pay for it or not? Is it free?
Yeah, free. But you need to wait for the queue to execute your job. Yeah. I may choose I will execute it on both a simulator and the real quantum computer. Like
this is IBM, right? This is the website.
Right. Let me first do it on a simulator and submit the job. We later to see the results. And again on a real quantum computer, like choose Manila. Yeah, we can back to see all the jobs. You can see the real computers, they are pending in queue. Expect to run in 90 minutes. But the simulator already done. We can see the results in 1,024 experiments. 508 of them have the outcome of 0, and 516 of them are in status 1. If we increase the
trials, right?
number of shots, yeah, it will eventually converge to 1 by 1 fraction. Yeah, its idea is like the Monte Carlo simulation, right? I'm back to see this. I hope we can get these results before we end this.
So basically, we just need to draw and attach on the panel, and the qubit programs will be synthesized automatically in the right.
Yeah. Of course, you can write in Qiskit, in Python, or using the quantum assembly language. But because nowadays the quantum programs are very simple, so it's more convenient to just drag and drop those programs, like those integers programming lessons using like PC logo language.
Yeah, so basically, because your introduction is more towards assembly level, right? So we need to understand and whether we need to turn a qubit into superpositions and when we do the measurement. Yeah. But for I just a little bit curious, maybe I just raised a question too early. What is a high level language supposed to represent, right? A variable assignment or a function call or switch the variable value, etc.
You mean the H-gate?
I mean that in the programs, for example, and here we just into a very low level, just like classical bits, right? If we want to switch the bits, we may need to put we may load some value from memory to registers, and we do the calculation and put the value back to the memory. So this is what the low level classical binary programs would do. But in high level, we just say that we have a variable there and we switch the variable, and that's just all.
Yeah, it's a very interesting question. So how, you mean how we can implement this?
So example, basically, I think some, I have now some professors in UCLA, and they have already proposed a set of the interpreter and the compiler. They provide a high-level languages. And I think in UCLA, there are already some undergraduate student course to learn how to using a high-level programming languages for writing a quantum computing program. Yeah, basically, I just want to understand the semantics, but maybe I raised a question too fast. You can keep going on in terms of this assembly level, superpositions, and a measurement, etc.
Yeah, okay. Let me continue. Okay, so another very interesting properties of the H-gate is it's like the minus will get a positive. If we create a superposition, and after that we put it into another H-gate, it will return to the certain.
What is this dash means?
Oh, this dash is simply it's like the comments. It separates those for.
Okay, basically it's just a knob something.
Yeah, and actually when compiling the program, it will
ignore it.
Separate those two parts of randomness using different or random seed.
Sorry, separated than what?
Yeah. So the different parts on both sides of the dash line, it follows independently randomness. It's like we're using different random seed for both sides.
Which means that this gate
that means if we don't use the dash line, those two H gate, like when we simulate them, they are using the same random seed, like 5. And if we separate them using those, this is a barrier, it will follow its own randomness.
And what do you mean by follow its own randomness?
I think it just means they would use two random seeds to make the two random.
Yeah. In
processes.
simulators,
I got it.
So that promises
so
that make
they
sure.
will show different behaviors, right?
Yeah.
So when we have a barrier there, so the result will becomes non-deterministic. However, if we
nope, even we have a barrier here, if we go through a H gate and then another H gate, it will returns to its state, its certain states of zero. You can like we now, if we do not do the measurement, we can see if we only have one H gate, the probability, not frequency, the probability of those possible states are 50-50. And now we got another H gate, it will back to 100% zero. And if we add a NOT gate, it will be 1. You understand?
Okay,
so
let's keep going on.
It's like we not and not, it will become nothing. Yeah. So that's the idea of so that's the basic idea of the how we create qubits and how we measure it. So the other components in the composer, like this is NOT gate, is a C NOT gate for create the entanglement. Those gates is for the phase operation, and the if is like if. I think now Yufan can give a more complex demo on the growth algorithm.
You're done?
Yeah.
Okay.
Yeah, I just give some basic ideas on how we.
Yeah, I think it's quite interesting. But I think it's better for you to prepare or illustrate the semantics of each operator, right? So I understand that you got the, for example, if I'm going to raise a question, once we have put some variable, some qubit into superpositions, we introduce probability, right? And what if we have two qubits? And if we have two qubits, if we turn those two qubits into in a superposition states, and what's supposed to be?
Let me just give a quick demo. If now we got two qubits, you can see in the Q sphere, we'll now have 0, 0 and 0, 1. It's easy to understand, right? The first zero is means the right. Now we
superposition.
If we got 2, 0, and it will be 0, 1 because the this no.
Yeah, and how these how the qubits in their superposition states are added, removed, or changed during the computation.
Yeah. Why it's called the hard-mark gates? Because you can see its idea is very similar to a hard-mark product, right? And if we now do a C, it's called C NOT gate. This will become a very classic demonstrate of the Bell test. You know the Bell test? In 2016, even the researchers done a experiment called Big Bell test. They basically they gather like 1,000 or 10,000 or 1,000 people around the world and using application internet application. So in the same time, they can freely choose whether they prefer 0 or prefer 1. So the researchers believe humans humans' thoughts are genuine randomness. So they can use those humans to simulate to build a real quantum computer. So So this build has explained the idea of any local hidden variable must be correlations that beyond classical. Anyway, I'm not very familiar with the physics series behind that.
But whatever it is, I think there's no need for us to go deep into the physical property. We just need to know the rule of the law, physical law, and based on the law, we just build our own computing systems, and that's all. So here, since you can see, what I understand is that now each variable, it looks to me like a dimension, right? It's more a dimension, and each dimension will has a probability. Sometimes for one variable, a qubit variables, it will actually high dimensional vectors, and each dimension indicates the probability, right? For being what value. And we are performing two random variables, right? If I understand it correctly.
Yeah. As I mentioned before, the superposition is like the idea of a linear combination of the vector space. So
you mean adding together those two qubit variable?
Yeah, we now have 3 qubits, so we got 3 digits of the quantum. You can see it's a quantum vector. So if we have both superpositions in all 3 of them, three of the quantum registers, we now have how many?
Probability, right?
Yeah.
How many possibilities? Right? How many possibilities?
Yeah, those I think is why.
And so when we adding for anyway, so suppose the variable consisting of 3 qubits, it means that it is actually a random vector or random variable consisting of 8 dimensions, and each dimension indicates a probability. So here the probability is just equally distributed among all the.
Yeah, because it's probability, not frequency.
Yeah, I understand. It's even probabilities. Here is the even probabilities across all the 8 dimensions. So is there possible that we adjust the probability, for example, some dimension is much just like apply software.
You raised a good question. Yes, as I mentioned in you remember the very complex graph before. So the idea is how we design a quantum algorithm is that we encode those problems into the faces in those qubits. So like for a quick example, if we add
sorry, so minor questions, how to define the faces of each qubit?
I'm not very familiar with how to mathematically define them, but the idea is we can encode those problems to the faces, and we can do inferences with them. No, not inference, interference with them. So those
so it means that the qubit is not independent anymore.
Those qubits or those amplitudes are in phase will add and be amplified, and those other phases will be cancelled. It's the idea like the
I don't get it much of you. I need an example to crystallize your statement. Yeah.
Let me show an example of how
it's a headphone, right?
Yeah, it's a headphone. We need some ideas. Like, it's like we have ambient noise, and we got a processor, and if we want to cancel the noise, we just create an exact after phase amplitude or the wave that can be because those two sound waves are exactly out of phase, so they can cancel each other. So the idea is similar in the quantum sphere. So we can do this processing using the interference, and we get our desired results from those signals that are added and amplified.
Okay, I somehow got it. So
Yeah,
so you mean that when we using some anyway, so the phase canceling technique, we can create a qubit variables which have a more variational probabilities, right? In different dimensions. Well, for example, sometimes the probability of some dimension will be canceled out. The possibilities, right? The possibility of some dimension will be canceled out. Am I right?
Yeah.
Okay, right. So maybe we can have more examples. So, so here I suggest the Changsheng. So you raised a very good examples, and I'm not sure how much time you put it. If I were you, I would prefer to crystallize or provide concrete semantics of each operator, and in your slides, maybe some animations can help. Can also be help. Maybe okay, that's okay. Now you're going to move to Yufan for more examples.
Okay, Yufan, it's your turn.
Okay, let me share my screen. So I will introduce algorithm. The traditional algorithm is just the search algorithm. The specific element was searched in an unsorted library. So we, for traditional algorithm, we just have n ON algorithm. For the details, like we need a log n bit register and an incubator and a comparator. And for example, if we have 16 numbers, we use a 4-bit. Sorry, we use a 4-bit register to represent the number, and the numerator will change the value of the register serial numbers from 0 to 15 turn and send them to the comparator one by one. So the simplest way is just to follow the sequence and compare each, and the time complexity will be ON. But for the quantum algorithm, it's called Grover algorithm. It will only cost square root n time. And the basic idea is that, for example, there is the lucky wheel you want to, you want to try. For example, here is $10,000. Here is only $1. Here is $100, and here maybe is $1,000. And you want to choose the $10,000. So for the quantum algorithm, it will amplify the probability of 10,000 this part, and to make you more possible to choose the 10,000 part. So formally, this question can be formalized as you have a abstract function fx that accepts search item x. If the item is a solution to the search task, then fx will equals to 1. If it's not, this will equal to 0. And sorry. So we will go to the how the algorithm.
A minor suggestion here. When you're given a slice, I suggest you digest the word and turn it into some bullets and the dimensions here. I just feel that your slice consists of too many words here.
Yeah, I actually don't prepare slides before, but I think I needed to review Changsheng said, so I just prepare slides just
now, right?
Yeah. So for the qubits, a digital bit has only 2 states, either 0 or 1. So if it is 2-digit bits, there are 4 states. There are 0, 0, 0, 1, 1, 0, and 1, 1. So, but for the qubits, it's much more complicated. Not only qubits can be certain state like 0 or 1, but also can be 0 and 1. This means superposition of 2 states. So this is terminology superposition states. Changsheng has mentioned that. And for the quantum state, we first put it loosely. So we didn't consider all the complex number field. We just consider the real number field. The difference from a digital bit is that it has 2 possibilities. That is, it may be 1 or 0. When the quantum is mentioned, it will collapse to different states with different probabilities. For example, the current quantum state of a quantum is that the probability of 0 is 1/4, and the probability of 1 is 3/4. So this is a quantum state. When you mention it, it will collapse to a state with different probabilities. And what is the probability? In fact, the probability is just a representation. It's not actually the probability. The quantum state is actually the weight sum of each value state. That is, each state is multiplied by its own coefficient and then summed up. These coefficients are complex number. It's not real number. It's not probability. It's called probability amplitude. In order not to involve too much mathematics, here we just use the real number domain. So here are some basics about the cubics. So we go to a bit deeper. Here we first goes to the grounded state. So here I needed to write something, so you can check my screen on my phone. Could you see the screen?
Maybe you can. So you need to combine both your phone videos and the slides, right?
Yeah. Because I didn't prepare. I just prepare some, some notation and mathematics, because it's a bit needed to write because there are too many formulas.
So you're going to handwriting all those formulas by yourself?
Yeah. So
okay,
here,
sounds impressive.
Okay, so here we first, could you see my?
Yufan, hello Yufan. I think you better change your audio to your phone, so the speakers will show up in the Zoom.
Maybe I can just stop, and then you can choose.
Is that possible? Okay, you can try to
choose my screen. Yeah, you choose my phone screen. Could you see my? Okay.
I mean, you can mute your computer and unmute your phone. So
I think I can hear it clearly, but my suggestion is in Zoom, I suggest everyone will switch to the speaker view instead of the gallery or full screen view, and giving the speaker view. And I think his paper will be clearer.
I think you need to fix my phone screen to your first screen. Then you will just.
Or I can pin your.
Yeah. So we go to details. First, we can now we in a real number field. So we just use our 2 number to represent the quantum state. Here, the alpha is for the 0 state, and the beta is for the 1 state. And there is the restriction that.
Yufan, will you please move your camera to the left? Yeah. Okay, that'll be fine.
Yeah,
so maybe we need to find a way to build a camera. But anyway, he says this works. Okay.
Okay. So there is a restriction. So alpha square plus beta square will be 1. Okay. So here we represent a quantum state is alpha and beta. Here we restrict to the real number field. So we didn't consider the imaginary number. And then for so one quantum state can be represented as.
You mean this one? The one quantum state means the state of 1 qubit, right?
Yeah, 1 qubit. 1 qubit. Qubit. The 1 quantum state for 1 qubit.
And by the way, the constraints of alpha square plus beta square equals to 1. Is this some rules according to the physical law, or
Yeah.
okay, so that means given a okay, so but how does Changsheng to get a 0.5 or 0.5?
Because he consider alpha square. This is maybe the 0.5 because
Yeah.
this is you know.
But 0.5 square plus 0.5 square equals 0.5, right? Not one.
Whole as the 0.5. Yeah.
All right, got it. I got it.
Actually, alpha beta is not probability. It's not probability. It's called probability amplitude. I just mentioned. So it's not probability, but it's called probability amplitude. It's different. And now we can consider alpha square as the probability. We can consider as this meaning, but it's actually not that meaning.
Okay, so and also you mentioned that alpha and then beta could be a complex number instead of real number, right?
Yes, it can be in complex.
That means according to the physical law, by right, alpha and beta are supposed to be complex, and there's the imaginary part.
No. Here, alpha beta is the real number. We only use two real number to represent one qubit quantum state. But if there maybe you can use alpha, beta, gamma. The gamma may be represented as the complex of the imaginary number.
But what does it mean, and why?
It's x, y, z. The z may be the imaginary, and the x, y is the real. X,
but
y.
anyway, the alpha, beta, gamma is actually represents the probability of whatever it is. It represents the qubit state, right?
Yeah, the qubit state.
And it means that the state can be represented by either the real number and the imaginary number. Oh, yeah. Sorry, the real number and a complex number. And for the complex number, so here I'm going to confirm that the parameter gamma is actually a complex number, or it is an imaginary number.
Imaginary number. If you add an imaginary number in the real number field, it will become the complex number field. For example, here maybe Z means gamma and X means alpha, Y means beta. Then there will be a point in this complex number field. But now we didn't consider gamma because it's too complex. So we just consider the real number field. Okay.
Maybe the complex is used for mathematical analysis, but overall, alpha, beta, gamma just for a different dimension, right? Just to describe different dimension.
Maybe.
This right. So, by right, the one qubit can only represent with two dimensions. That means once a qubit has 3 dimensions, the additional dimension is supposed to be imaginary. Yes or no?
I don't know. I didn't consider the complex number.
Okay, so maybe we can have some series of discussions about these. But anyway, so for today, we just look into the real number, and each qubit will have 2 dimensions, and each dimensions are represented with 1 real number.
Yes. Okay. So a quantum state can be represented alpha, beta, and it can be a combination, linear combination of 1, 0 and 0, 1. So this is the base state. So here for convenience, we just write this as base state. So this is a direct symbol, and this is for the column vector. Any question here? So for example, we calculate the inner product.
So basically we set either alpha or beta to be 0, right? But one to be 0, another must be, or another one alpha beta to be 0, that means another number must be 1.
Yeah.
Right. Okay.
Yes. So for example, the inner product can be calculated as this formula because this means the row vector and this means column vector. So it will have calculated as a number like an inner product. Okay. And if you
sorry, so here the alpha is actually
why is alpha? I just show some symbol.
Here the alpha, the A here, so it's not alpha and beta, it's A and B. And for on this B supposed to be so can you be more specific of the inner product? So here can you be also more specific about the what the A and B means? A is a variable, B is a variable.
This is not this topic. This inner is just a cosine. You can just consider this a cosine, two vector, and you can compute the cosine similarity. And the cosine similarity actually is the inner product, and this is the inner product. That's the AI multiply BI. A is a vector that may be A1, A2.
I understand. So here, what's the relation between A and B as a vector and this reset operation of 0 and 1?
This is just a symbol. I just for convenience we use this symbol to represent this quantum state. This is a quantum state. Yeah. So here I just introduce another computation method for I prepare some questions. So I just want everyone understand this symbol.
So this symbol, this symbol, for example, the B means that okay. So these two dash here, so A double dash B. This double dash is actually, you mean you're introducing definition. This is a definition, or this is just an inference or lemma, etc.
It's definition.
Okay, so that means giving.
This symbol means column vector. Column vector.
Column vector. Okay.
This means row vector.
Okay.
Yeah. For example, for this symbol, we can say this is a column vector 0, 1. This is a column vector. And for this one, this is a column vector. So this is also a symbol, and we can just define this for convenience for my later mathematics. So we can use this symbol to compute that's the inner product, because I think everyone knows the inner product. If I write it
I got it. So this
multiply with a row vector multiply with the column vector, it will get a number.
So it means that the letter will get a matrix, right? N times n. The matrix with shape of n times n.
No, that will get a one number because it's,
no, I mean the later one, the latter one.
This.
Yeah.
Yes. Okay, so everyone got it.
Okay, at least I got it. So maybe anyone have a question here? Okay, if no question, let's keep going on.
Yeah, so maybe I write it here, write it down. Okay, I think these are basic linear algebra. Let's review this. And now we can represent one quantum state as this formula. Anyone can get this formula? Okay, so there's another two symbol here. I will introduce why we use these two symbols later. This plus, this is a minus. So here is a question I prepared for you. What is this? What is this result? Anyone can answer this question?
And we'll have try. So we need any calculation for that, right?
Yeah, that's a simple calculation because it's an inner product. So
anyone would like to have a try?
I think it's quite, that's a basic linear
Yeah,
algebra.
maybe you can further write down into a vector form so people can easily to calculate it, and you can point out an audience for that.
Okay, maybe maybe Darren, are you
Yeah, Darren, are you still following?
Do you mind writing it out in vector product in the vector form first for the plus and minus?
Yeah, so maybe you can help Darren to write a vector format. So basically, this plus operation will be actually be turned into a special vector, right? So maybe we can write down it. So so Darren can be easier for Darren to do the inner product.
Yeah, it's quite simple. It's just you just add this here, add this.
Yeah.
So this just the.
Yes.
So in the product will be.
Yeah. So Darren, so I think the answer is supposed to be straightforward now. It's an inner product, so it's supposed to be a scalar.
Oh, sorry. Then it should just be the norm of this vector. So it should be half.
It should be the inner product. So one times one minus one times.
That should be a value, right? Why is it product?
Yeah. No, it should just be half, I guess.
No.
Yeah, it's supposed to be the cosine. You can calculate the cosine of these two vectors.
Sorry.
So that means there's two orthogonal vector, right?
Yeah, it's just a 0.
Yeah, because cosine value, the cosine of the two orthogonal value of vector will always be 0.
Yes. So another here, I think this will be also very clear. This also be 0.
Move your camera a little bit left.
Okay.
Yes.
Yeah. So you can just think in the geometric. These are two, vertical, and this is also vertical. Can you imagine this?
Basically, orthogonal. Basically, yes.
Yeah, they are all vertical vectors.
Okay.
So these are some basics. Then we go to 2 qubits. If there are 2 qubits, then we will define the symbol like here. Be careful, I write. Okay, so here is quite different. It not means, for example, the 0, 1, you cannot say 0, maybe 0 is 1, 0. And the 1, you can say this is 0, 1. But it's not concatenate these two. It's not concatenate, it's different. So be careful about this. Okay, so here we will consider if we have 2 qubits, maybe 5, 0, this is alpha 0, 0 plus beta 0, 1. And another qubits. So if we entangle these 2 qubits, and the
entangle or combine?
Entangle.
Okay.
Now there are 2 qubits. Yeah.
So you're talking about the quantum entangling.
Yeah. Now it will calculate by the tensor product in the linear algebra. And here is the formula. So here is just the formula. You just remember this calculation. In linear algebra, it will this part.
Is that all the combinations, or is there a standard property in the superscript? So the beta 1, beta 0. Okay, that's fine.
Yeah, this is a job called tensor product in the linear algebra, and you can just imagine this is for 0, 0. This is for this is for 0, 0. This is for 0, 1. This is for 1, 0. This is for 1, 1. Okay. So now it also satisfies the restriction because you can compute by here. I can compute here. You can compute that they will also equals to 0, equals to 1, because you just like here alpha 0 plus beta 0, beta 0. This is 1, and you can compute here. It's also 1, and it will also calculate get 1, because you know alpha plus alpha square plus beta square will be 1. So you just use this formula and we'll find out this result. So it will also satisfy the restriction.
Okay. Interesting mathematical property.
Okay. So and some, you know, there are some properties of the tensor product, like A tensor product with B is not equal to B tensor product with A, but this is satisfied. But it is not important for today.
Right? This is a linear algebra property, right?
Yes, it's linear algebra.
Mm.
I just mentioned here. So here we must to understand the first is this base state. The base state is just the unit state is just 0 and 1. This is base. And then we have a superposition. This is a linear, you know, combination of 0 and 1. So in formula, we will regard as alpha and beta. Okay. No question. So here we will get another formula. It means pure state. Pure state is just this quantum is just a combination. They're not entangled. There are some, you know, this is phi. So this phi has some weight and to combine to a new state. But this state we also consider as pure state. So these states are also pure state. They are not entangled. Means these qubits are not changed simultaneous.
So it means that each qubit, so the impure qubits means that some qubits are actually entangled with each other or not independent, right? The pure means independent.
Yeah, pure means independent. These qubits are not entangled with each other.
Okay, so in this case, is there any constraints that Wi, sigma Wi is equals to 1?
Yes, I just mentioned for this part.
Okay.
The phi 1, phi 0. Yeah, but then we will introduce the entangled state, and you can also think that, like, for example, it's just like so it's have 0.5 you will have 50% to become phi 1 and 50% become phi 2. It's not a combination, but it's a probability. Okay, so this is the entanglement.
why it was called entanglement?
First, entanglement means that these qubits will change their vector simultaneously.
So entangle means the subjects of the entanglement must be at least be 2 qubits. Am I right?
Yeah. Yes.
So here the so-called entangle is that you are talking about the entanglement of phi 1 and phi 2. It means that for given a qubit, it will be either phi 1 or phi 2.
Yes.
And their probability is actually 50-50.
Yeah. Yes.
Okay.
Okay. So then we goes to the gate. We just Changsheng also mentioned some gate. I will also introduce the gate. For example, the X gate. S gate means just like the negative gate. They just change the alpha beta, change the
Switch alpha beta, right?
for example, after the X gate, it will go to. So for another formula, it will like X influence this qubit, so we'll get this formula. And in linear algebra, this is just here, this matrix. So you can see that in quantum programming, you must have something about some knowledge about linear algebra, because almost all the gates has some formula of the linear algebra. So there are 3 formulas.
Why it is a matrix instead of a vector?
It is transformation, basically.
Oh, transform. Okay.
It's transformation. Any question?
So the left part should be. Oh.
You can just think the matrix.
So given a qubit alpha beta, if we apply X gate, it from the sense of linear algebra, it is just equal to have these X times that alpha beta vector.
Okay.
So we got a beta alpha. So this gate is basically a linear algebra matrix, and each matrix is basically a transformation in the high dimensional space.
Yes. So for example, X on this vector, it will get to 1, or X on this, it will get the same. So just remember what I said about the.
We still need to memorize. This is supposed to be, there's a 2 square root, 1 over 2 square root, and 1, 1, right?
Yeah, so 1, 1 is the same.
Yeah, so.
So if this will be minus, because here is 1 minus. Okay.
Okay.
So then we will go to another gate, the H gate just mentioned about the Changsheng. H is Hadamard gate, is a very popular gate. Here we goes to the sphere, or I think Changsheng also show you this, but now we goes to we go to just we not go to the 3-dimension, we just goes to the real value, so it will become a circle, not a sphere. Okay.
Okay, so I got it. So in this case, the so-called sphere, because there is imaginary dimension there.
Yeah.
Right.
So the y is the y is actually the imaginary axis. Yeah. So we don't count the imaginary.
So by the way, so if we include the imaginary dimension, it means we will need to satisfy alpha square plus beta square plus gamma square equals to 1.
Yeah, I see.
I see.
Yeah.
Just my guess. I don't know. Okay.
Yeah, because it's a sphere, because so the radius will be 1.
So the sphere. Okay, let's keep going.
Okay. So now we can represent 1 alpha beta on the geometric meaning. So we can as this T point P, and this is theta, and this can be represented sine theta 2 and cosine theta 2.
Okay.
Yeah, so here the representation is alpha equals cosine to theta 2 and beta equals to sine theta 2. Okay, so now we do H gate on this point. We can see what's the result. Here H point do influence on this quantum bits phi, and you can see you will write the formula here. So that's the any question for this formula?
The Hamad operator.
Yeah, I forget to introduce the Hamad. This is H. This formula is like this. This matrix. Okay. So maybe I can write it down. So for example, this matrix multiply with 1, 0. This is 0, and then it will get 1, 1. So it's alpha plus beta. So if so we'll get 1 minus. Okay. So this is for this is for 0, is for 1. So this is alpha minus beta for 1, 0, and alpha minus beta for 1. This is for just a linear algebra computation, and this will get to here. Any question? Yeah, you just use linear algebra to compute just this formula.
Okay, let's keep going on.
Okay, so then
H, by the way, is there any questions here?
So H is just this transformation.
Yeah, I just asked the audience any question here. If no question, let's keep proceed. So the Hamad operator is basically I think it's a way to calculate to distribute the value across the dimension, right? So this basically a way.
I have another question. Why is sine theta over 2? Why is not sine theta?
Yeah, basically it's right. The theta, maybe you write it wrong, right?
You
have the over. Huh?
We define that for later mathematical convenience.
You define that?
Yeah, we define.
So I think Xianglin is asking whether the theta.
So theta is this.
Yeah. So
is that the correct theta?
The radius is 1, then I'm not sure what is the
So right, the theta equals pi, right? So
yeah, I write it wrong. It's 2.
Yeah,
Okay. Then
yeah. So for theta 2 is for later convenience, so we just use theta 2. And then you will now you can see the 1, 0 is matrix to this formula, and then you will add this part to this formula, and then after mathematics, you will get this result. Yeah, after mathematics, because there's a formula in the tangular. I can't check here. So you can see the previous it is cosine theta 2, and now change it to cosine pi 2 minus theta. So actually this is how to say, this is
By the way, so where this
So
the pi over 2, where the pi over 2 comes?
because you can compute use the formula.
So
Theta minus plus cosine to sine to theta is actually their formula. But I forgot it. You can check. Yeah.
Assuming you're correct. So let's keep going on. So basically, you're talking about it when we have the Hammett operator. So we somehow, my gut feeling is that the Hammett operator is basically just distributed the values to redistribute the values based on a Hammett matrix, right?
Yes.
Somehow way to redistribute it, but we redistributed it with a rule based on the alpha plus or minus beta over 2 square root. Yeah, but anyway, let's keep going on. So suppose we have such a property of redistributed the probability over the dimensions, and then what do we have?
Yes. So this is the geometric meaning of the Hammett gate.
Oh, wait a minute.
I thought there are some. Let me check. Okay. Should be theta to 2 pi minus theta. Yeah, this is the geometric meaning of this.
Okay.
Yeah, so this is just from the x, z will change their position. So there will be x, z, not the original. It will change position. It's just some meaning in the geometry, but I quite not very understand. But this is the why is we use the Hammett gate, and the Hammett use the Hammett gate. Will be many properties. Maybe this is not very accurate, but this formula is very accurate. And like the X gate, I just mentioned. So this formula we will use later. Okay.
Okay, let's keep going on. So
compute the linear algebra. It will give you the result. And then we will go to 2 qubits because now we just mentioned 1 qubit. If it's 2 qubits, it's quite different. Not quite different, it's a bit complex. To follow the specification I just mentioned here. So if there are 2 qubits, and then they will go through 2 Hammett gate. That means you can say this is. So this is 2 qubits, and they go through a Hammett gate. And then what is the whole state of the whole qubit state of the whole system? It will be computed like I just mentioned. The tensor product. Remember the tensor product. So now we go to the H gate on this whole system, and this the result will be this formula. They are all linear algebra, so I not go to the detail of the linear algebra. Okay, they are all linear algebra. They are we just remember this formula. It's okay. Then we will go to another gate. This is an important gate called the CNOT gate. In this gate, if the input is the it's just like if statement in the in our program language. For example, this means 1. So if the state, because if you go to a H gate, you will 50% become 0, 50% become 1. So if get 1, it will flips the number here. So there will be 2 results. There is 1, 0, 0, and 1, 1. I just think Changsheng mentioned. Any problem here?
So the operator, the operands of the C node is 2 qubits or 1 qubits.
2 qubits.
2 qubits. So given 2 qubits, the C node is basically the semantic of the C node is basically whether these 2 qubits are with the same alpha and beta.
Yes, the original is just 0.
Mm-hmm.
That means it is 1, 0.
Mm-hmm.
1, 0. And then use this gate because the first gate, this qubit goes through a H gate. Then it will go
become 0.0.5, yeah.
Yeah. So if the first 0.5, it will go output a 0. Then it will not flip the second.
Do you need a measurement there? Because it's already 0.5, 0.5. And why do it becomes 1?
You don't need a measurement. This is just a gate. This gate will, you know, this is just the entangle. This is the basic of entangle. Because they entangle each other, so the result will not be 0, 0, 0, 1, 1, 0, 1, 1. It will change together.
So here.
So for the first 0.5, it will output 0. Because this is 0, so it will not flip. So they will also output 0. But for another 0.5 possibility, if it is 1, then because it is flip because it's 1, so it will flip the number. So it will output the 1. So it's actually the basic entangle.
So it's not pure anymore.
Yeah.
So here the alpha, so let me clarify. So given the alpha, so we have the alpha equals 0.5 and beta equals 0.5 after we applying the.
No. Different. I mentioned here. This is possibility. Okay.
Okay, I got it.
But alpha beta is not possibility. Alpha beta is possibility amplitude. And you can consider alpha square is a possibility, but it's quite different thing. Yeah.
So that means this gate is basically an entanglement, right?
Yeah.
So given this, that means after this entanglement, so that means we apply an entanglement operator after we apply the Hamilton operator.
Yeah.
Am I right?
Operator is not entangled. They just
so after we apply the Hamilton operator, the qubit is still a pure qubit. But after we apply the entangle, and the qubit is not pure anymore.
Yes.
And here we'll please more specific on the semantics of C node. So once we have the an arbitrary qubit, and after we using the C node, the qubit will becomes entangled. That means, by the way, so I still have a question here. So in this, once it is not a pure method, once it's not a pure qubit, whether the rule that alpha square plus beta square is still equals to 1.
For 1 qubit, it will also equals to 1.
But here you write 0, 0, and 1, 1.
This is quite different. I should write it very strictly. Actually, the result is here.
Hmm.
Yeah, this is actually a vector, and we can represent as a 0 because for convenience, it's actually 1, 0. Okay,
Hmm.
and it's 1, 0. So this is alpha, this is beta. Alpha is 1, beta is 0. Alpha is 1, beta is 0. So the alpha square plus beta square is also 1.
Hmm. I got it. I got it. Now I got it. Okay.
Yeah. Okay, no question here. So then we goes to the algorithm. We first go back to the slides. So the first we have a review on the gate. There are different metrics means the transformation on the state. Okay, so these are influence the alpha beta. It will goes to another alpha beta. And this is X gate, is the H gate. And here we goes to some example. Here, you can see this white means 0. So if you use this, it will be, this is the H gate, and this will be a C0 gate. And when you is 0, it will output 1 because this 0 it flips this number, so it will goes to 1. So the result will be 0, 1. And another result is this 1, 0. It will not flip the second qubit, so it will output 0. So they are all 50%. Any question here?
Okay, let's keep going on.
Yeah.
Oh, by the way, is there any question here?
No, because it's a bit complex, so I didn't prepare.
Mm.
Yeah, if it's black.
No, I'm asking the audience whether there's a question here.
Okay. Any question here?
Okay, if there's no audience, no questions, let's keep going on.
Okay, so this is, if there's a black node, then it will output 0, 0, and 1, 1. I just mentioned they are all 50% probability. Okay. Then we will go to the algorithm. So remember, our question is that we needed to search a number in such a number. So we have many numbers like 0 to 100, and we need to search a number that satisfies fx equals to 1. So this is the question, it's a search problem. So the algorithm is that we first use the comparator to flip the specified state. This specified state is just the x, what we want the x, and then we use the amplify to amplify that specified state. So this is the idea I just mentioned here. We just amplify the one state, what we want, the state we want, and then execute the first and the second in a loop. So the specified state will be large and large. The possibility will be large and large. Then we will just observe the qubit, and there will be just the
observation. Does that means we need to have a sample? That means we need to. The point is that we need to measure it for several times, right? Not just one, because you just amplified it. You don't remove the possibility of the other choice, right? So for example, at the very beginning, so all the numbers, all the values are kind of the probability of all the numbers are equal. So we each time we observe it, it could be equally to be the other value. But after we apply the amplification, the probability of the largest value keep increasing, but keep increasing does not diminish the other probability.
Yes.
So what that means, we need to observe for multiple times.
No, we just normalize the probability.
Yes, we do normalize the probability, but there's some multiple.
I don't know.
But so
observe
maybe I'll let me confirm. So these algorithms is deterministic or non-deterministic?
not deterministic.
Yeah.
It's
So it's probability. So that means if we want to do this, if we want to make sure we have the correct, we search the correct value, we need to measure it for multiple times, or at least we need to run it for multiple times. Am I right?
We don't need to measure multiple times.
Yeah, another time, each time we run, we measure it once. But once we get
this two step in this loop, we don't need to measure it. We just amplify the.
Yeah, I understand that we do not need to. I'm saying that's the last steps.
Yeah,
so here we executed a step 1 and step 2 for maybe 100 times in a loop. Okay.
Yeah.
So each time we executed it, we got a number. Am I right or not?
Not got a number. We don't know. We totally don't know the qubits. We just ask
so
the qubits.
sorry. So after we execute 100 times, so it means that we amplify 100 times.
Yeah.
So, and after we got these times and we got a state, and then we observe the qubit. Observe means measure.
Yeah, mentions that.
Right. Yeah. So for example, so in this case, we're supposed to have a probability to be wrong, right? So, but after we applied it for 100 times or amplified it for 100 times, the chance to be wrong is very, very small, but it still have a chance for us to get wrong.
Yes.
Yeah. So my point is that, so suppose we do not want to amplify so many times, we maybe we run the algorithm for multiple times and to see to take the vote, to take the majority vote of the solution. You get my point? So for example, we have Grover algorithms and we run it once. It told us that the result is 1000, and run a second time, it tells us the result is 100, right? So we run the algorithms for 100 times. We take the majority. We take the value with the largest frequency. You get my point?
I don't think it's so. I think it's not okay because it's not for frequency, because if you run for one time, it will get low probability, but for second time, it will do a higher probability. So maybe 4 times, then it will get a very high probability. So the final result will be the final result.
I think you get me wrong. So let me confirm. So suppose we just run the loop for 1 times, right? So and we got the result. The result have a probability to be wrong. Am I right?
Yes.
Right. So anyway, so that means this Grover algorithm just to amplify the chance of be successful, but it is just to increase the chance. It cannot guarantee that we will sample the once we apply the measurement, we cannot guarantee that it actually will unlikely got the wrong answer. Am I right?
But if you observe it, you will not increase the probability.
Yes, we just observed it. So you can see, so after we amplified it, the probability of us to sample the biggest value is very high, right? So let me make sure. After we apply the measurement, we just got a value. The value is just one of the probability.
The probability will not increase if you measure multiple times.
I understand it will not be. So it's just more like we throw a dice, right? So suppose the dice. So the amplification is just, for example, if the result of the dice turn out to be 1, we got a 1,000. We got $1,000. but if it becomes 2, we got $100. Okay, so if I understand it correctly, the second step, that means use an amplifier, is to keep increasing the chance for us to get the dice to be 1.
Yes.
Right. So, but there is still a chance that even if the chance to make the dice to be 1 is very high, but when we throw the dice, there's still a possibility that we can have the dice of 2. That means get only $100. Am I right?
Yeah.
Right. So my point is that given the Grover algorithms, we can just amplify the for multiple times. That is the formula times in a loop. But if we want to get a more accurate result, we probably can run the algorithms for multiple times. Run the whole algorithms means that we run step 1 on 2 step 4 for multiple times.
Yes, but no need.
I find that maybe it is the same that you're just increasing the loop in step 3. So basically they're the same.
Yes. I think they are no, I don't think that's same, because the amplifier, if you run this multiple times, the probability will increase in a different way. Not like you run the whole algorithm for like 4 times. For example, you run this loop 4 times, and then you run this algorithm, and this loop you only run 1 time, and this algorithm you run 4 times. This two is quite different.
Yeah, I understand. So if we don't apply amplify at all, running multiple times of algorithms does not help at all, right?
Yeah.
And okay. So I think this is fairly clear. But anyway, so I may still need to digest a little bit, especially for the mathematical part. And also the semantics of the entangle. That's part I still need to look more into it. But anyway, I think Yufan did a very good job. Both Changsheng and Yufan did.
I needed to also introduce the algorithm. This is a basic. I needed to.
Yeah. I suggest that we have some follow-up. So for this week, Changsheng provided an overview and showing the tools, and Yufan provide a few semantics. But I would prefer I really appreciate that you can write everything down through the handwriting. So it's really appreciated. It means that you have a very solid foundations, at least a memory foundation for all the semantics. But I hope that we can have a slice. We can have the slice, so that we do have the video. But once we have the slice, people can go over your slice later and to pick up the idea more frequently. If there's enough expertise built among the group, maybe we have a chance to step into the research of the quantum computing. Maybe not that deep, but we can have a test.
Okay.
Okay.
Do I need to introduce the algorithm?
Maybe not for today, because I think we are quite short of time. But I think we can arrange the other meetings, and also since there involves some mathematics, so you can provide some quiz or exercises for people to practice. Okay, thanks a lot for today's. I think we can call it a day for today's meetings. And thanks everyone to join us, and thanks Xianglin, Changsheng, and Yufan for the great preparation. Okay, bye.
Bye.